Um, it's my pleasure today to introduce our colloquium speaker, Dr. Nan Liu. Dr. Liu is a candidate for our astromaterials and solar system formation position. She has traveled all the way from St. Louis, Missouri to speak with us today, where she's a research assistant professor in the Department of Physics, where she has been since 2018. She's also a faculty fellow of the McDonnell Center for Space Sciences and holds a third job as a Carnegie Institute investigator at Department of Terrestrial Magnetism. So she's a busy woman. Before coming to the WashU, she was a postdoc as a Carnegie Fellow at the Department of Terrestrial Magnetism from 2014 to 2017. Before that, she graduated with her PhD in 2014 from the Department of Geophysical Sciences at the University of Chicago. And prior to that, she got her BE in 2009 in Environmental Sciences from the School of Earth and Space Sciences at the University of Science and Technology of China. Nan's research addresses questions in nuclear astrophysics as well as cosmochemistry, using a suite of advanced laboratory and microanalytical techniques to analyze terrestrial materials. Her work has been noted by winning the 2021 Near Prize from the Meteoritical Society. The Near Prize recognizes outstanding research in meteoritics and closely allied fields by young scientists. So with that, I give you Dr. Nan Liu, who will be talking about cosmic forensics using presolar dust. Take it away, Nan.
Thank you, Jeff. Let me share my screen first. All right. You hear me okay? All right, perfect. So thank you for showing up after the technical issue. And today, in this talk, I'll show you how we can do cosmic forensics using presolar stardust grains and exactly what cosmic forensics means. So in this follow video, what we are going to say is an overview of the events that happened in the past 8 billion years. So we will walk back in time. So before the existence of life on the Earth, the Earth was once a molten hell. This is not a place where we want to be. And here we see a moon is forming during the giant impact, and we don't know where that lunar material is from. And in the early days, it is chaotic, and we see the formed planet is being bombarded by leftover planetesimals all the time, changing its chemical composition. And now we're back to the disk, and this is the protoplanetary disk, and we see a planet is forming. And before all of that, we're just a mixture of dust and gas, and these are the remains of old dead stars. And in the molecular cloud, the gas to dust ratio is about 100, so it's mostly that gas. And we're going to go into the molecular cloud, and here this is the birthplace of the solar system. Here stars are being born and die constantly, and they replenish the cloud with the metals they produce during their lifetimes. Here we see a star just went off, and they're pulsating all the time. So the Earth wasn't alone. And here we have the supernova remnant, and the bright star we were seeing is the neutron star left over from the supernova explosion, and now a supernova is exploding. So supernova explosion is believed to be the driving force for star formation, and possibly including the formation of our own solar system. And before it explodes, it is once a red giant star experiencing all kinds of fusion reactions to produce rock-forming elements for us later. And now that massive star is forming. And this is what happened over the past 7.6 billion years before and after the solar system formation in the local interstellar medium. And we're in the product of this grand evolutionary process. So we know in our solar system, the sun only burns hydrogen to make helium, but we have metals on Earth and across the solar system. So these were inherited from previous generations of stars that contributed materials to the local interstellar medium. So one of the questions that always intrigues me is how element productions in stars affect planetary formation. Also, for the sun to form, for the protosun to form, so a part of that dense molecular cloud had to collapse. So what was the trigger of that collapsing? A popular hypothesis is that this was triggered by a nearby supernova explosion. So one of the focuses of my research is to search for ground truth evidence to test this hypothesis. And here is just an overview of the universe evolution. So we say over the past 14 billion years, the universe passes through these distinct eras and vast ages. And at around 5 billion years ago, the sun was born. And it was made from a mixture of dust and gas present in the local interstellar medium. And part of that dust grains were not destroyed during the evolution of the solar system. And later they were present in the extraterrestrial materials as these microscopic presolar stardust grains. So one of the most efficient way to find presolar stardust grains is to dissolve a piece of primitive extraterrestrial materials in strong acids. Then this way we can dissolve away solar system materials, and these different presolar phases can be concentrated in the acid residues. And this method is known as burning down the haystack to find the needle. And to identify these presolar grains, what we can do is to do isotope analysis. So in these images, what we see here is in the center, we have a silicon carbide grain. And if we check its isotope composition, we see it has twice amount of the carbon-13 and 3 times the amount of nitrogen-15 compared to the surrounding solar system material. So these are the signatures of say and no cycle during in stars. So the oldest presolar grain has been determined so far is 6 billion years. So presolar grains serve as the only witness to this wide range of stellar and planetary processes in the local interstellar medium over the past 6 billion years. And what is even wonderful here is that they also recorded the composition of their parent stars that were born at even earlier times. So they are bona fide stellar materials that can provide us ground truth information about the origin and evolution of the solar system. It is a field for creativity because here we see the grains recorded a wealth of information, but the challenge is how we can decode each of the messages independently. And this brings cosmic forensics. So what we want to do is to find the fingerprint of each of these events. So presolar grains recorded the information about the evolution of the solar system. So in the solar system, we have these different, 2 different types of meteorites, and they have different isotopic compositions. These are not caused by processes occurring in the solar system. These are stellar signatures. It is still a hot debate, so why the solar system has these 2 different isotopic reservoirs and why it was persistent in the disk. But fundamentally, these differences are caused by the heterogeneous distribution of presolar grains across the protoplanetary disk. So knowing the distribution of presolar grains in a wide range of extraterrestrial materials can provide us ground truth information about dust transport in the early solar system. Presolar grains also recorded information about the birthplace of the solar system in the Milky Way. So over time, we know the Milky Way becomes more and more enriched in metals because of metal production in stars. So naturally, we expect young stars in the galactic disk to have more metals to build their rocket planets than old stars in the halo, and this chemical variation must have contributed to the diversity of actual solar systems observed so far. The thermal evolution of rocket planets depends on the heat input from these three short, long-lived radiogenic isotopes, potassium, thorium, and uranium. So we expect the concentrations of thorium and uranium in the mantle to vary by orders of magnitude between planetary systems because they are produced by a rare stellar event, the rapid neutron capture process. So it is important to understand the birthplace of the solar system in the context of galactic chemical evolution so that we can truly understand the difference between the solar system and actual solar systems. So in this talk, what we are going to do is to go back to 5 billion years ago and to investigate the birthplace of the solar system in the local interstellar medium through the eyes of presolar brains. We're going to see what types of stars contributed materials to the solar system and what we can learn by studying their bona fide stellar materials. So we'll start with the SProcess and AGB stars. So we know for elements heavier than iron, they cannot be produced by fusion reactions because iron has the highest bending energy. So these heavy elements are made by these three stellar nucleosynthesis processes: the slow neutron capture process, the rapid neutron capture process, and the P process. So the S process operates along this zigzag pattern in the nuclide chart because every time when it reaches an unstable isotope, it undergoes beta minus decay. And this is because the neutron density is really low, so it has a very slow neutron capture rate. So every time it undergoes beta minus decay, and it results in this zigzag pattern. So the S process operates along the value of beta stability. Different from the S process, the R process operates in a much higher neutron density environment. So it can continue to capture neutrons until the beta minus decay rate exceeds the neutron capture rate. And then it undergoes continuous beta minus decay until it reaches a stable isotope. So these two processes are responsible for making 99.9% of the heavy elements in the solar system. But we see we have a few isotopes on the left side, and these are the P process isotopes. But the P process is not a single process. It is a combination of multiple processes. And we don't really understand the P process because the only information we have is their abundances in the solar system. Their abundances are too low to be detected in stars. Then it comes the AGB. So AGB stands for asymptotic giant branch, and it is an evolutionary stage undertaken by all low to intermediate mass stars late in their lifetimes. So an AGB star experiences alternate shell hydrogen and the helium burning, and it results in this layered structure. So current stellar models predict stars with initial masses between 1.5 to 3 solar masses can all become carbon-rich in the envelope during their AGB phase. And these carbon-rich low-mass AGB stars are going to be the focus of this talk. So in the AGB stellar envelope, we detected these line features, and these are in fact the absorption lines of element technetium. This is very peculiar because if we check the nuclide chart, we see technetium has no stable isotope. So to explain this observation, it requires in situ production of technetium inside the star. And this points to the S process because we see during the S process path, when it reaches molybdenum 99, because of the slow neutron capture rate, it undergoes beta minus decay to make technetium 99. So these are the absorption lines from technetium 99. And this is a solid piece of evidence that links the SProcess to AGB stars so that we know the SProcess operates in AGB stars. So how does SProcess exactly operate in AGB stars? We can use 97 molybdenum as an example. So the change of its abundance over time can be expressed by this equation. So this is the neutron density. This is the thermally average neutron capture cross-section. It can also be written this way. And this is the abundance of an isotope, 97 or 96. So we can say it can be produced by neutron capture onto 96 as expressed by the second term, and it can also be destroyed by neutron capture onto itself to make 98 as expressed by this first term. And then we can define a parameter called tau, and this is the neutron flux integrated over time. And we can think of tau as an evolutionary parameter for the SProcess. Then we substitute dt with the expression for tau, and then we end up with this new equation. So since this is an evolutionary parameter for the SProcess, when the SProcess reaches a steady state, this term goes to 0. So we end up with sigma n value being a constant for the SProcess. And this is the basic theory for the SProcess. It can be tested against the solar system SProcess pattern using this diagram from Capilla et al. 2011. So the y-axis is the product of sigma n plotted against the mass number. All these squares are pure SProcess isotopes, which means they can only be produced by the SProcess. And when we connect them together, it forms the SProcess path. What we see here is that we don't have a global steady state, and especially at these two local regions, it has a large step, a large decrease. But within these two local regions, it reaches approximately a steady state. So the lack of a global steady state is mainly caused by these two bottleneck isotopes along the SProcess. So they have magic numbers of neutrons, so their nuclear structures are very stable. They don't like to capture neutrons to make other nuclei. As a result, neutrons are stuck at these two bottlenecks to boost their own abundances. It's very similar to the situation when the number of lanes on a road is suddenly dropped. What we expect is cars get stuck at this bottleneck, so we have a heavy traffic. So this bottleneck results in huge productions of strontium-88 and barium-138 by the SProcess. And this is why we have these two SProcess peaks at strontium and barium for the solar system abundances. We also have another SProcess peak at lead because lead-208 is doubly magic. It has magic numbers of neutrons and protons, and that's why we have this third peak here. So the analysis of the solar system SProcess pattern leads to the conclusion that we need this kind of neutron density for the SProcess. And because this carbon-13 alpha N reaction can release neutrons of this neutron density at relevant AGB temperatures, we know this is the major neutron source for the SProcess. And we also know the SProcess operates in this zone below the convective envelope. And this zone is called the Helium Intershell. It is in radiative condition, and it is full of carbon-12 because of the interior shell helium burning. So, and above it is the convective envelope full of hydrogen. So to form carbon-13, hydrogen needs to move downward to react with carbon-12. So for several decades, it is believed that overshooting is the mechanism that is responsible for this partial mixing, because the convective envelope is full of turbulent eddies. And when an eddy reaches this boundary, it will overshoot into the helium intershell. So on the right, this is the radial profile along this direction, and it's in mass coordinate. So this is our helium intershell, and this is the envelope. So hydrogen is brought downward into the helium intershell because of this overshooting mechanism, and it is believed that its mixing velocity follows this exponential decay. So the important thing here to remember is that beta is a free parameter, and it can be adjusted to bring different amounts of hydrogen into this region to form different amounts of carbon-13 for the S process. So once hydrogen is here, it reacts with carbon-12 through this chain of reactions, and carbon-13 is formed, and then it reacts with alpha particles to release neutrons for the S process to occur in this region. So this helium intershell is full of carbon and S process products. And at the end of shell helium burning, because of the large amounts of released energy, this convective envelope, convective boundary moves inward, so that the carbon and S process products can be brought up to the surface. And this process is known as this third dredge up event. So here we see the nature is really kind to us because it exposes itself for us to observe. Although this S process occurs in a deep layer, because of this event, so the S process product is brought up to the surface, so we can observe the envelope composition to figure out how the S process operates. And this is why we can observe a technetium at the stellar surface, as we saw earlier. So an AJB star experiences strong stellar winds and mass loss from the surface. This mass loss rate can go up to 10⁻⁵ solar mass per year. So the gas is lost from the surface, cools off, and we see dust grains condense out of the gas. So over time, the envelope becomes dustier and dustier and cooler, and we will see the spectrum moves from red to infrared features over time. And in the circumstellar envelope around an AJB star, we can observe this 11.3 micron feature, and this corresponds to the formation of silicon carbide dust. So here we see these silicon carbide grains recorded the S process compositions of their parent AJB stars. So here we come back to this problem of carbon-13 formation mechanism. As I said earlier, so this overshooting mechanism can bring hydrogen inward to react with the carbon-12. But then the question is this the only mechanism that operates along this convective boundary and be fully responsible for this partial mixing? So we know a star is rotating and also may have a magnetic field, and we naturally expect multiple physical processes could operate along this boundary. So to test whether this is solely responsible for this partial mixing, we need to have sensitive observables to test the model predictions for the S process. But not every S process isotope here is sensitive to this partial mixing mechanism. Why? Because we discussed the S process theory, this sigma n value remains constant in most of the regions along the S process path. What this means is if we consider the ratio of two isotopes produced by the S process, it is fixed. It is fixed by their neutron capture cross sections. So even if we have a large amount of carbon-13, it can lead to increased productions of these two isotopes. Their increased rates are always the same, so that this ratio is fixed. So this is not the kind of fingerprint we're looking for to constrain the formation mechanism. What we really need to know is the abundances of these two bottleneck isotopes. Because as I said, here and here, it did not reach a steady state. And come back to our traffic analogy. So if we want to know the number of cars get stuck at this bottleneck, we need to know the rate of incoming flux and also the number of cars on the road. So the abundances of strontium-88 and barium-138 should be most sensitive to the carbon-13 distribution in this helium intershell. What we also want to know is the abundances of nickel isotopes, because these are the seeds for the SProcess. And in our traffic analogy, this would be the number of cars at the beginning. So this set of information should provide us the best chance to explore whether overshooting is the mechanism that is fully responsible for the carbon-13 formation, the major neutron source for the SProcess. So I was motivated to measure the strontium and barium isotope ratios in silicon carbide grains from AJB stars. So these grains were extracted by acid dissolution of a primitive meteorite called Murchison. So we extracted these grains and we first analyzed the grains with the nanosims for these isotope ratios, because this kind of information allows us to directly compare the grain composition to AJB stellar envelope composition, because we have such observations. So based on such comparison, we can figure out which grain came from AJB stars. And then after we found our AJB samples, I analyzed these grains using a different type of mass spectrometer called resonance ionization mass spectrometer. So to measure strontium and barium isotopes, I used 4 different lasers, and by tuning the wavelengths of these laser beams to match the atomic structures of strontium and barium, I was able to measure all the isotopes of these 2 elements without any atmospheric interferences. Also, in the next slide, we're gonna have a look at the nickel isotope data. And this was taken from the literature collected by someone else, but also using a RIMS instrument. And before we move on to the data, I want to point out that the combination of these 2 different types of mass spectrometers allows us to measure the isotopes of most elements in the periodic table in microscopic stardust grains. And here comes the data. Strontium, barium, and nickel isotopes. The grain data are shown as black dots with 2 sigma errors, and then the AJB model predictions for the envelope composition are shown as lines with the symbols. So the symbols are the carbon-rich phase where silicon carbide grains are expected to form. So this is the same AJB model, but they adopted different beta values to have different carbon-13 distributions. What we see here is that this standard exponential carbon-13 formation can't really explain the data. Although this beta value here provides a good match to the data for strontium and barium isotopes, we see this is the model that lies the furthest to the grain data in the nickel isotope plots, and vice versa. So for in several decades, for the first time, we provided the first piece of solid evidence that overshooting induced mixing alone does not work. And at the same time, a group of physicists in Perugia, Italy, worked on the theory of magnetic buoyancy. According to their analytic derivation, so in the presence of magnetic buoyancy, the mixing velocity has a power law dependence on the distance from this convective boundary. And this is very different from the exponential decay caused by the overshooting mechanism. So without going into the details of this magnetic buoyancy mechanism, what we see here is the consequence of this process. So it can bring hydrogen deeper into the helium intershell and form the carbon-13 also has a flattened distribution profile. And this is because of the power law dependence here. In the overshooting scenario, we see the exponential decay results in the carbon-13 concentration quickly drops to 0. Since this doesn't work, so we implanted this formula in the AJB model to see if this improves in the data model comparison. And bingo. So these are the same AJB model, but they just adopted this magnetic buoyancy formula for the carbon-13 formation. And these different models have slightly different parameters for that equation. we see that these models provide a much improved match to this grain data here. Also, it explains why the grains show such tight distributions with very little variation. Because of this parallel dependence, now it reduces the sensitivities of these isotope ratios to the distribution of carbon-13 in the helium intershell. So the grain data implies that this mixing velocity should have this parallel dependence instead of an exponential decay. And because current physical models predict magnetic buoyancy is the only mechanism that can lead to such a profile, so the data is in favor of this mechanism. And after we published our results, our conclusion was further tested and confirmed by other groups using their own stellar codes. So this conclusion is not dependent on the stellar code. Now you may ask me, do AGB stars have the magnetic field strength as inferred from the grain data? Unfortunately, we don't have really good data for low mass AGB stars, but we do have good data for many white dwarfs. So white dwarfs are the leftover cores of AGB stars after they lost the entire surface materials. And here's the distribution of the magnetic field strength measured for many AGB stars. So this is our inferred data, and it lies at the lower end of this distribution. So first of all, it is allowed by the white dwarf measurements, but we do see some differences. But we don't know if the magnetic field strength evolves over time and whether it has any dependence on the initial stellar mass. So we really need to have good measurements for low mass carbon-rich AGB stars to provide stringent tests on this magnetic buoyancy scenario. On the other hand, if magnetic buoyancy is responsible for the carbon-13 formation, it should have other consequences on stellar evolution and nucleosynthesis. So based on this physical model, it predicts that these magnetic flux tubes can directly carry carbon-rich helium intershell materials to the surface without any mixing. And when these tubes break, it directly releases this carbon-rich material for silicon carbide grains to condense. So the consequence of this scenario is that you can form carbon-rich dust grains while the envelope is still oxygen-rich. And indeed, this has been observed for a few AGB stars, and this provides a solution. In addition, the physical model predicts that during shell hydrogen burning, this magnetic buoyancy process can also operate, and this can greatly enhance the production of these isotopes while reducing the production of oxygen-18. And this is indeed has been suggested by presolar grain measurements and also some stellar observations. So this one process can solve 3 problems for AGB stars, so it looks quite promising. And in the future, we can also collect light and heavy element isotope data from a single grain and see if their inferred magnetic buoyancy strengths are consistent with each other from different perspectives. And this should provide a very stringent test to this scenario. And at the end, we can also speculate a little bit about the perspective of recovering PLL magnetic field strengths recorded in presolar grains about their parent stars. We have magnetite grains from AGB stars, and this is a ferromagnetic material, and it could have recorded the magnetic field strength of their parent stars. And we have this type of quantum diamond microscope with very good spatial resolution. So it may be a fun project to try some presolar grain measurements to search for the PLL magnetic field strength. If it works, and we can provide the first ground truth evidence about magnetic field strength about AGB stars. So to quickly summarize here, so in this first part, we had a look at the nickel, strontium, and barium isotope ratios of AGB stars, and then the data ruled out the overshooting as the main mechanism responsible for carbon-13 formation. Instead, the data are in favor of this magnetic buoyancy scenario. So thanks to magnetic buoyancy, the SProcess was able to work in AJB stars to produce a lot of rare earth elements for us. And thanks to the SProcess and the rare earth elements in our electronics, I'm able to talk to you virtually today. Our inferred magnetic field strength is allowed by white dwarf observations, but in the future, we can further test these hypotheses by doing more presolar grain measurements. And also maybe we are able to recover the paleomagnetic strength, so stay tuned. In addition to AJB stars, type 2 supernovae also contributed their materials to the solar system, and type 2 supernovae are believed to be one of the main driving forces for star formation and possibly including our own solar system. So as phrased by the French writer François Rabelais, nature doesn't induce sudden mutations without great violence, and this exactly describes the role of type 2 supernovae in governing the evolution of the universe. This is a pre-supernova massive star at its blue supergiant phase. It is a little bit hotter and brighter than its previous phase, red supergiant. We see the faster wind caught up with the slower wind, and this made this dense rain of material. So the star continues to evolve and eventually explodes. And in the center, that pristine material cools off from millions of degrees and a lot of gas condensed into dust grains. So type 2 supernova is a prolific dust producer in the universe, and its dust grains carry distinct isotopic signatures. A group of presolar silicon carbide grains are called X grains. They're called X grains because they have exotic isotopic positions. And the titanium-44 is a smoking gun that links X grains to a type 2 supernova origin. A pre-supernova massive star has this onion shell structure because of fusion reactions. So fusion reactions occur in a star to counter gravity and prevent the star from collapsing. So it starts with hydrogen and then helium and processes up through the periodic table until a core of iron and nickel is produced. It stops here because these iron nickel isotopes have the highest binding energy. So the star is run out of fuel. The gas collapses onto itself, and the sudden compression of the inner core results in a outward expanding shock wave. Then a type 2 supernova explosion occurs. So it takes a few seconds for the star to collapse, and it takes a few hours for the shock wave to reach the surface. And when it passes through these different materials, they're heated up to from in the inner region is up to 10 to the 9 Kelvin at the beginning, and on the surface is 10 to the 6 Kelvin. And in the next slide, what we're going to say is the chemical, the predicted isotopic composition along this radial direction for the supernova remnant. So this is our radial direction, and these are the predicted isotopic compositions after the supernova explosion in the supernova remnant. So the supernova remnant maintains this onion shell structure because the 1D model did not consider mixing during the supernova explosion. And you may be questioning this simplified picture because this is what we observe for supernova remnants in space. It has a quite complex structure, not a simple onion shell structure. And this kind of structure is can be produced by state-of-the-art magnetohydrodynamic model simulations. But the challenge here is how can you use this observation to constrain this model? It has many uncertainties. And we're talking about microscopic dust grains and comparing microscopic dust grains to such simulated ejecta that are tens of orders of magnitude larger. It's pretty much like comparing oranges with apples. So we still prefer this simple 1D model to help us understand the composition of a grain. But we still have to consider mixing to explain the grain data because we know the grains are condensed in a mixed gas because they have a wide range of isotopic compositions. So what people did in the past is to do this ad hoc mixing of calculation for each grain to figure out its mixing recipe. So they can randomly pick up materials from these different zones to see if it can match the isotopic composition of a grain. So you may immediately notice the problem here. We have too many free parameters, and normally we don't have enough isotope information to constrain these different parameters. So in other words, we have too many degrees of freedom to provide any quantitative constraints on the supernova evolution and nucleosynthesis. And this greatly limited the scientific value of supernova dust grains. So in contrast to this ad hoc mixing approach, in my 2018 study, I showed that one can look for correlations between isotopes. The idea is that although X grains condensed in a mixed gas, in the gas, we have different types of isotopes, with each type being produced by the same nucleosynthesis process. So instead of focusing on working a mixing recipe for each grain, what we can do is to look for correlations between isotopes that are being produced by the same nucleosynthesis process. And just to give you an example, so in this inner layer, it produces pure silicon-28 and titanium-48, and these are both alpha isotopes, and they're always being produced at the same time during the supernova evolution and explosion. And in comparison, in this outer zone, it produces neutron-rich isotopes during the explosion, and silicon-30 and titanium-50 are both neutron isotopes, and they are always produced together. And based on this idea, I decided to measure silicon and titanium isotope ratios in supernova dust grains. And these data were taken with the NanoSIMS instrument. So our new data in blue together with literature data point out a negative correlation between titanium and silicon isotope ratios. And in fact, this corresponds to a positive correlation between titanium-49 and silicon-28. And silicon-28 is the denominator isotope here. And so when we extrapolate this correlation to minus 1,000 per mil in the x-axis, it means we have no silicon-30. It is pure silicon-28, and we see it points to this inner silicon-sulfur zone. And what this intercept means is the titanium isotopic composition of this inner zone. Although in this approach, we did not work out a mixing recipe for each of the grain, what we did is based on this correlation, we subtracted the contributions from all these outer layers, and then we were able to derive a quantitative constraint on the titanium isotopic composition of this specific zone. And with this extrapolated value and its 95% confidence band, we can directly compare it to the model prediction for this specific zone without considering any mixing. We see the model predicts this ratio to increase over time in this silicon-sulfur zone because we have vanadium-49 in this zone and it's radioactive. It decays to titanium-49 over the course with a half-life time of 1 year. So the comparison of grain data with the models led us to conclude that the grains must have condensed at least 2 years after the supernova explosion. And this constraint from our study is in line with the observations for a few supernovae over the course of a long time. So these observations, mostly conducted with ALMA, confirmed that the majority of dust grains are produced later than 1,000 years after the supernova explosion, consistent with our result. What this means is that at the beginning, the gas was really hot. It's millions of degrees, and it takes time for the gas to cool off in order for dust grains to condense after 2000, below 2000 K. And this tells us about the thermal evolution of the supernova, of these different supernova remnants. It's great that we can figure out this timing, but the real question is how we, but it doesn't tell us fundamentally how dust grains are produced in a supernova remnant. And this kind of information can be studied by analyzing the lattice structure and chemical compositions of supernova dust grains. So plotted here are the Raman data for silicon carbide grains from low mass stars and the supernovae. The low mass star grain, the AJB stellar dust grains are just shown as a density map here. And we see, although they're all silicon carbide grains, they have different Raman features because of their different stellar condensation environments. So this is the first solid piece of evidence to show that different stellar condensation environments can lead to different crystal structures. To understand why they have different Raman features, we can use a different technique called transmission electron microscopy. And based on such studies, we can work out the detailed dust formation process as illustrated by this cartoon here. So this tells us how fundamentally how dust grains are produced after the supernova explosion. So it has been proposed that an infrared light flux between 5 and 8 micron observed for several supernovae are caused by the presence of iron carbide and silicon carbide grains in the supernova remnants. And James Webb is superb in making measurements in this wavelength regime. So I think it's an exciting time to find more unique silicon carbide grains and their subgrains with diverse chemical compositions. And if we can obtain infrared spectroscopic data from such grains, we can directly guide the future detection of dust grains in the supernova remnants. Supernova dust grains also provide us a unique opportunity to investigate a wide range of stellar nucleosynthesis processes because during the explosion, it is quite complex and it has varying conditions. Given the very low abundances of P-process isotopes, so presolar grains provide us the only opportunity to investigate this poorly known process beyond the solar system. It is so important why didn't people do this before? Because the supernova dust grains are extremely rare. But fortunately, I developed this method a few years ago, and this greatly reduces the analysis time and cost. Now it is possible to identify a large number of supernova dust grains for more detailed isotope and structural analysis. So as I said, the combination of these two different instruments allow us to probe almost the full periodic table, and there have only been only a limited number of elements have been examined. So each isotope and element has its own story and is waiting to be discovered. And this kind of analysis will allow us to answer one of the most fundamental questions in the field of nuclear astrophysics. Where do P and R processes occur? Do they occur in type 2 supernovae? And to quickly summarize, in this section, we saw we can use radioactive isotopes to constrain dust condensation timing and their structural compositions. It tells us information about the physical chemical conditions after the supernova explosion. So given this new opportunity for finding supernova dust grains, there are a lot of work waiting to be done. We can do a lot of structural and isotopic analysis to better understand the dust condensation and all these different interesting stellar nucleosynthesis processes. And finally, I just want to point out the presolar grains also allow us to trace the evolution of the solar system, although I don't have time to talk about this. And in this recent study, we were able to use the presolar grain abundances and also primitive organics to trace the aqueous alteration and also thermal history on the surface of Vesta. So in conclusion, presolar brains are exciting because they enable the study of bona fide stellar materials in laboratory, and they provide ground truth information about the origin and evolution of the solar system. So we know AGB stars and type 2 supernovae are the dominant sources that contributed their dust grains to the solar system. They also contributed the majority of rock and life-forming elements to our solar system. And a type 2 supernova may be the reason why we're here. It possibly triggered the solar system formation. Their stardust grains present in the solar system are time capsules. And in this study, in this talk, we saw we can decode the different messages by studying the different properties of their stardust grains. There are still many open questions left to be answered in the future, and I believe we will have better capabilities to better decode these messages in the future because of the rapid development of nanotechnology. So we have this new method of identifying supernova dust grains. The RIMS instrument has a sensitivity more than an order of magnitude higher than the previous RIMS instrument. And the signal to noise ratio of Raman mass spectrometer is increasing every day thanks to these new optical fibers. So I'm sure we will have better answers for some of these questions in the very near future. So thanks for your attention, and I'm happy to take any questions.
Thank you, Nan. That was a really exciting talk. It's neat to see how you can use presolar grains as a ground truth for stellar evolution models and be able to rule out models based on their hypothesis and the samples that are in the lab, and that you can also see with hopefully JWST and Hubble in the future. All right, I see Jonathan has a question. Go ahead, Jonathan.
You're muted.
You're still mute. Or
muted.
Yeah, you can hear me. Okay, yeah. So you were talking about the magnetic field of white dwarfs, but the problem I thought was to raise material from the deep layers of asymptotic giant branch stars. What do we know about the magnetic fields of AGB stars?
That's a very good question. We don't really know. So that's why I think we need to have better observations and indirect evidence from presolar brains in the future. So there have been some measurements at the surface of an AGB star. So I think the magnetic strength there is on the order of 100 to 10 to the 4th Gauss, and it's within the range of what we need, but that's on the surface. We don't know the strengths at that specific layer, at this specific evolutionary stage. So yeah, it's a good question. So I think we need to have better observations in the future directly for low mass AGB stars. We need to have 3D magnetohydrodynamic model simulations. So if we can observe the surface, we have still to inform the magnetic field strengths in that particular layer at that specific time. And then on the other hand, I said, so we can measure different isotope ratios of presolar grains. The light isotope ratios are affected by magnetic buoyancy during shell hydrogen burning. The heavy element isotope data of these presolar grains are affected by the carbon-13 formation in the helium intershell. So these are in different locations, in different processes, and it would be interesting to see if the informed magnetic field strengths are consistent or inconsistent with each other. I think there are a lot of interesting questions there waiting to be investigated.
Katrina, I see your hand up. Go ahead.
Yeah, hi. Very nice presentation. So many things to think about. And it's truly amazing how many new discoveries have been made. Just to remind the audience, the discovery of technetium happened in the 1950s, and that actually stimulated all the work on nucleosynthesis, especially for the SProcess. And I think what that discovery was for nucleosynthesis is now just emphasized and even made more strongly by the discovery of presolar grains. And I think all the nucleosynthesis models that we have are now taking the presolar grains as ground truths. My question to Nan is, the problem, it seems to be, we are mainly looking at silicon carbide and a few selected other compounds. I know it's very difficult to find presolar grains. And for example, one thing is there's a discussion of iron carbide, and that was an old prediction that we made in the 1990s. And we quickly revised that it should be iron silicide. So my question is, what other materials are actually being looked for, and what other presolar materials might be still sitting around, because we are clearly not living in a galactic disk that is carbon rich and dominated by silicon carbide. But what other presolar grain materials do you think you can discover in the near future, and what is the search for the predicted condensates? I'm really wondering, there must be more hiding out there, but what do you think we can do in the near future?
Very good question. Thank you, Katerina. Silicon carbide is my favorite just because they're relatively large, they're structurally stable, and when we analyze isotope ratios in the right way, we can avoid the contaminations, so we can get an intrinsic stellar signature, which is really important. For other phases like graphite, it's structurally activate. So what happens is, a lot of time when you measure the isotope ratios, it's a mixture of stellar composition and solar or asteroidal or terrestrial composition, and it just complicates things. What we need to do is to have a fundamental understanding of the isotopic compositions of silicon carbide grains, and then when we move on to other phases like graphite grains, we can truly know the difference. And also we have oxide grains. I think they're also interesting. They're relatively large and they can be extracted by acid dissolution, and corundum grains, they're structurally stable. So this is something what we can do in the future. But the problem there is, the solar system is oxygen rich, and even in the acid residue, you have solar corundum grains sitting with your presolar corundum grains. It just takes time. We just need to have students to work on it. And regarding your question on the new phases, a project I always interested is to search for new presolar grain phases in the acid residues where people found bulk isotopic anomalies. Like molybdenum isotopic compositions, we know it's probably carried by silicon carbide grains, but there's also this recent study of strontium-84 enrichments in some acid residues. I think that's the place where we want to go and look for new carrier phases. And this also goes back to the question of the carriers for the isotopic anomalies at bulk planetary scales. I think everything is connected, and we have the technique. And yeah, I'm interested in doing it. Sure.
Just to follow up, do you think it will be possible to do this kind of trace element analysis in the major, in the most massive contribution of presolar grains, which would be magnesium iron silicates? Do you think it will be possible to get all this detailed information out of presolar silicate grains? Because I think that would be even more to the ground truth, but I don't know what the technical problems would be.
What do you mean? I don't think I get your question. You mean like magnesium, iron, and silicon?
Like, could you measure trace element abundances and isotopic composition in presolar silicates?
We can use the OJ nanoprobe to do that. Yes. So yeah, that's what we have been doing. So first we use nanosims to find these presolar silicate grains based on their oxygen isotopic anomalies. And then we go to the next lab, the lab next door, and use the nano OJ probe OG nanoprobe. Yes, and we can characterize the major element concentrations like magnesium, iron, silicon. So sometimes we also find the oxide grains, like the magnetite grain I was showing you. So that was based on OG analysis, and then people did TM analysis. Yes, so we can do that kind of an analysis right here.
Could you get strontium isotopic compositions?
No. It's way too low. No. Okay. Yeah, we still probably need to wait for another 10 years.
Okay, thank you.
Well, until that breakthrough, we'll have to take Brad's question.
Hi, Nan. A wonderful presentation. Thank you. Right there on the open questions on your last slide is an intriguing one. How many supernovae contributed their material to the solar system? I'm curious, what are your thoughts on what kind of measurements or what kind of materials, what do we need to do to gain ground on that question? Is it finding different kinds of presolar grains like Katharina just alluded to, or better precision in aluminum 26 and iron 60, an agreement in those systems? What do you think we need to do to actually gain ground on this question?
Very good question, Brad. It's a very broad question. So I'll try to answer it to my best knowledge. So I think, so from my perspective, well, what I want to do is to do heavy element. So first, here we just talk about type 2 supernovae. We also have the Stardust grains from other types of special supernovae like type 1a supernovae, and also maybe electron capture supernovae as also observed last year, really in space. So we also have this special type of supernovae, but here we're just thinking about the type 2 supernova explosion. And so first, we have supernova silicon carbide dust grains. We can analyze their heavy element isotopic compositions, and these kind of data can really allow us to constrain the explosion energy, because for that element, it's way too complex, and the isotopic compositions depend on many different processes. So heavy element isotopic compositions are preferred in constraining the mass and the explosion energy of supernovae, type 2 supernovae. So I think by getting this kind of information, first, what we can answer is how many types of type 2 supernovae contributed their stardust grains to the silicon carbide reservoir. But of course, maybe that special supernova that triggered our solar system formation did not produce any silicon carbide grains. They may have produced other dust physics. So we also need to do the same kind of analysis for other types of presolar grains from supernovae, and for other types of presolar grains. Sometimes we don't even know if they're supernova dust grains. So I think we need to use silicon carbide grains as the baseline to inform and to have that kind of knowledge to figure out which type of grains came from supernovae. And once we identify their supernova origins, then we conduct a heavy element isotope analysis. And if that is not available, we can do other multi-element light isotope analysis to answer the question, how many type 2 supernovae contributed to the graphite reservoir, the presolar oxide reservoir, the silicate reservoir. And if we go through the whole list of presolar grains and we see the same thing, I think it's a pretty strong evidence that maybe there was one supernova that triggered our solar system formation. And this is from the experimental aspect. But of course, we also have to know what kind of the supernova, type 2 supernova explosion, because it seems based on observations, only a limited amount of stars can become type 2 supernovae because there's observations for the inferred mass and the explosion energy. It's kind of limited, but the current data have large error bars and it's only available for a few supernovae. So I think we also need to have a lot of knowledge about what type of massive stars can become type 2 supernovae, and then we can compare our inferred mass and explosion energy from presolar grains and put it into the context and see if this is enforce one dominant type 2 supernova source. So I think we need inputs from different subfields, and it's a big question, of course. So, but we can really contribute to answering this question just by studying presolar grains.
Thank you.
And is there any way, like with presolar grains, kind of relates, I think, from Brad's question, if you have presolar grains from a type 2, can you potentially tell whether the grains came from different type 2 supernova, or can you only tell it's type 2 or AGB?
We can. So I think the three main types of supernovae are type 2 supernovae, type 1a supernovae, and then the electron capture supernovae. And we do find the dexter grains from all these three different sources, potential sources. And so for most of these X-rays, we can tell they're type 2 core collapse, type 2 supernovae, because they have very diagnostic astopic signatures, as the titanium-44 I was talking about. And for other grains, it's more ambiguous. For type 1a and electron capture supernovae, the main problem is we don't have really good stellar models to compare with the grain data. It's a understudied type of supernovae. But last year, there's this observation of electron capture supernova in space. I think there are going to be a lot of interest to develop such models in the future. And once we have more observations and constrain the stellar models, then we can really pin down if this grain came from this type of supernovae. We need to understand that there are different astopic signatures. Yes.
Okay, cool. Thank you, Nan. Katrina, you have another question?
Yeah, if I may, Brad brought up an interesting topic for discussion, and I'm now really curious. We know that there are certain probably supernova radioactivities were alive in the early solar system that are now extinct, and then there are signs of a supernova injection. Now, the interesting question is, if we had this short, now extinct radioactivities in the early solar system and they are ascribed to supernova, wouldn't we expect that the same kind of nuclides were also incorporated into presolar grains that formed around such supernova? And has there ever been made a correlation or a comparison attempt between extinct radioactivities seen in normal solar system materials versus presolar grains? Just wondering.
So I think the problem there is, so for the initial short-lived nuclides in the solar system, so it is diluted. So you have to consider this dilution factor. Then you have to know the chemical abundances of the supernova remnants, and then the chemical abundances of the molecular cloud from where the sun was formed. I don't think we have that kind of information for this kind of mixing calculations, but I do remember there was one paper to discuss whether a type 2 supernova ejection can explain the oxygen-16 difference between the sun and the asteroidal materials. I think the conclusion from that paper is so it calculated the dilution ratio and it was impossible.
Yeah, that's why I think that the models can predict a lot of things. So I really think we need either astronomical observations or astronomy with presolar grains to have the ground truth, as you were saying. So I think this work would be tremendously important for a variety of things. Thank you.
Thank you.
I don't see any more hands up. I want to take one last moment again to first apologize for the late start on today's colloquium. There was a little bit of a mix-up. And to thank you again, Nan, for Dr. Liu, for a great talk on presolar grains and how they keep us grounded. Have a great evening.
Bye, thank you.
Bye-bye.